We're going to do number 2 now, and what number 2 is asking you to do is use both the trapezoidal and the Simpson's rule to approximate the area underneath this curve. So really you're just going to be using those two different formulas that they gave you in this textbook. And I do have them off to the side here, and I did encourage you in the short lesson that you really should look over page 444 and see how they came up with the trapezoidal rule, why it works, because I really do believe that you can follow that algebra. So if you take a while to figure out why it really truly works, you will look at this as not so foreign anymore. Okay, so I'm just going to really show you how to plug and chug away with these formulas on the test. You won't be expected to memorize them, but I would give you this formula on the test. So if I ever ask you to approximate the area underneath the function by the trapezoidal rule, you will have this available to you, but you will be responsible for knowing what each one of these pieces mean. Okay, so back to the problem. Okay, so I have gone ahead and graphed this number 2. They gave me this. And so what I do know I'm trying to do is approximate the area from 0 to 1 underneath that's bounded by this function right here. So I graphed that function in orange, and then I also kind of just divvied up, or I sectioned off the area from 0 to 1 that I'm interested in. The next line of business is that I'm going to have to separate this into 4 equal pieces. So I'm going to go ahead and do that. Here is from 0 to 1. Alright, and I'm going to separate this into 4 equal pieces. So on this line, I'm going to just show this off to the side. It's kind of a blown up picture of that area underneath that curve. So this is that area drawn here, and what I've done is I've separated it into these sections. So really what you're drawing is these lines, and these form what we're kind of drawing and sketching in as trapezoids. They're closer than the rectangle rectangle approximation that we did before with these exact rectangular shapes. So what I'm going to say is this is x sub 0, x sub 1, x sub 2, x sub 3, and x sub 4. And so those are part of that equation, because what I'm going to be using is b minus a, so in other words 1 minus 0. So all of this is approximately equal to, by the trapezoidal rule, if you just plug and chug with that formula, you have 1 minus 0 all over 2 times, and then we got this 4. That's what we said n was equal to. We're sectioning this interval into 4 equal pieces. So 2 times 4. Alright, and then what we have to do is we're going to have to take, I'm going to leave some space here, but we have to have f of from x sub 0 all the way up until x sub 4. So I'm going to need a plus, and then I'm going to leave a blank here, or a little space, and you'll see why in a second. X sub 1 plus, I'm going to leave another space, x sub 2, f of x sub 2, plus, I ran out of room, so I'm going to go to the next kind of line here, and then all the way up to, this would be my last term because I've made it to the x sub 4. Okay, and then going back off of that formula that they gave us, how you would read this is when you set this up, you want to go from however many n values that you were given, from x sub 0 all the way up to f of x sub n, and then everything in between except for the 2 ones at the end. So f of x sub 0 and f of x sub n is disincluded from this, but you want to multiply it by 2. And once again, look over page 444 to see why that is. So I'm going to go ahead and do that. Here's my 2. Here's my 2. And I also needed 2 in front of my f of x sub 3. Okay, so now what exactly are these x sub I values? Well, x sub i's are going to be equal to your delta x times whatever I you're interested into. So we have seen this before. When you're looking at this, we called this C sub I in the past when we were doing the approximation of rectangles. But when you're looking at the subsections, what we did was understand that each one of these little increments from x sub 0 to x sub 1, this is what we would call delta x. So delta x, it's the width of these trapezoids, and delta x. Okay, so at this point right here, we don't want any delta x. X sub 0, the x value on this x-axis would just be 0. Here though, what is delta x? Because we want one of them. X sub 1 would be 1 delta x. x sub 2 would be 2 delta x's. X sub 3 would be 3 delta x's, and x sub 4 would be 4 delta x's. So x sub I would be given by this equation right here. You do have to be careful of this. I highly recommend that you draw sketches like I have done here. What I'm going to go ahead and do is calculate what is delta x. Once again, that will be given by your b minus a all over n. So it would be 1 minus 0 over 4, so 0.25 is what I'm going to say. Okay, and so now here's the thing, x sub 0 would just be delta x times I, so it's going to be 0.25 times I, which is in this case 0, so 0. X sub 1 would be 0.25 because it'd be delta x times 1. X sub 2 is going to be equal to 0.25 times 2, so x 0.5, and you would even see that on this x-axis. You can see that clearly. X sub 3 is going to be equal to 0.75, and then finally x sub 4 is going to be equal to 4. Just 1. Okay, so I do have to move this down, unfortunately. Okay, so I am going to be using this once again, but now I can plug in these x sub 1s, x sub 2s, x sub 0s, all of those. So I'm going to simplify this. We get 1 over 8. We have 1 over 8 times f of, and then 0, plus 2 times f of 0.25, plus 2 times f of